Imagine an infinite list of numbers, 1, 1/4, 1/9, 1/16, 1/25. Every term is the reciprocal of a perfect square. The surprise is, it involves pi. Watch how adding more and more terms makes the total sum approach a limit. If you add them up one by one, the sum grows. It passes 1.25, then 1.36. By the time you reach 1,000 terms, you're at 1.644. But then it looks like it stops moving. It hits a wall. For 90 years, beginning in 1644, mathematicians across Europe, including the legendary Bernoulli brothers, tried to find the exact value of this wall. They knew the sum converged, but they couldn't name the number it was approaching. Then in 1735, a 28-year-old Leonhard Euler found the answer. And it was a shock. The answer wasn't a simple fraction or a clean decimal, it involved pi. How does a circle's constant hide inside a list of squares? There are no circles here. No arcs, no radii, just whole numbers squared and flipped. To find out why pi is here, we have to look inside a wave. To solve the mystery, Euler turned to the Taylor series for the sine function. Most of us think of sine as a smooth, oscillating wave, but calculus tells us that sine is secretly an infinite polynomial. We start with x, then we subtract x cubed over 3 factorial, then add x to the 5 over 5th factorial. Once again, subtract x to the 7th over 7 factorial, and so on. This isn't an approximation. For any value of x, this infinite sum is exactly sine of x. Euler's genius was in realizing that if sine behaves like a polynomial, we should treat it like one. He started by dividing everything by x. This gives us the sinc function. Now look closely at that second term, minus a sixth of x squared. This coefficient tells us a lot about the function. Euler knew that in a standard polynomial, the coefficients are determined entirely by where the function crosses zero.
Where does sine of x divided by x cross 0? We know the answer from basic trigonometry. Sine is 0 at every multiple of pi. So the roots of our function are pi, negative pi, 2 pi, negative 2 pi, 3 pi, negative 3 pi, and so on. Euler made a daring assumption. He assumed that just as you can factor a simple quadratic like x minus 2 times x minus 3, you can factor an infinite series using its roots. He wrote the function as a massive infinite product of factors. 1 minus x over pi times 1 plus x over pi times 1 minus x over 2 pi times 1 plus x over 2 pi, and so on. When you multiply those pairs together, they simplify into quadratic terms. 1 minus x squared over n squared times pi squared. Now Euler had two different ways to describe the same function. One was the Taylor series from the beginning, and the other was this new infinite product. If they are the same function, their x squared coefficients must match. From the Taylor series, we know the x squared coefficient is negative 1/6. From the infinite product, the x squared coefficient is the sum of all the individual 1 over n squared times pi squared terms.
This leads us to the final equation. Negative 1/6 equals negative 1 over pi squared times the sum 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. Multiply both sides by negative pi squared and the world changes. Pi squared over 6 equals 1 plus 1/4 plus 1/9 plus 1/16, and so on. It was a masterpiece of intuition, but it was technically illegal. Euler didn't have a formal proof that you could treat infinite series this way. He was using analogy, not logic. It wouldn't be for another 100 years that the mathematician Karl Weierstrass would prove that Euler was, in fact, right. To prove Euler was right, Weierstrass showed that every infinite product like this has an extra fudge factor attached to it, an exponential function called e to the power of g of z. For Euler's logic to hold up, this entire extra term had to be exactly 1. And as it turns out, for the sine of x over x function, it was. Euler had been incredibly lucky. The factor was exactly 1, meaning his daring assumption wasn't just a guess. It was a hidden truth of complex analysis that wouldn't be fully understood for another century. The Basel problem wasn't just a one-off puzzle. It was our first glimpse at a much larger landscape called the Riemann Zeta function. Written as the Greek letter zeta of s, it's the sum of 1 over every natural number raised to the power of s. When s equals 2, we get the Basel problem, but Euler didn't stop there. He discovered that for every even number, the answer is a clean, rational multiple of pi. For zeta of 4, it's pi to the 4th over 90. For zeta of 6, it's pi to the 6th over 945. But the odd values, they are a total mystery. To this day, we have no closed form for zeta of 3, zeta of 5, or zeta of 7. We don't even know if pi is invited to the party. We've proved zeta of 3 is irrational, but beyond that, these odd powers are the dark territory of modern mathematics, waiting for the next Euler to find the light. It's easy to look at these formulas and see only cold, rigid logic. But to Euler, these weren't just numbers on a page, they were a melody. He found a way to hear the hidden music of the universe, proving that even in a list of simple squares, there is a circle waiting to be found. Mathematics is the only place where a guess from 1734 can become an absolute law of nature a century later. It's a language that doesn't care about time or borders. It only cares about the truth. And sometimes that truth is as simple and as beautiful as pi squared over 6. So the next time you see a pattern, don't just look at the surface. Look inside the wave, because the next great constant might be hiding exactly where no one expects to find it. Thank you for watching and keep exploring the infinite.